All right, everybody, let's get started, please. So the topic of today's lecture, there's a little bit about something called a T. So that's related to the pipelining stuff we've been talking about. And then the rest of the lecture is devoted to talking about file permissions. OK, so redirecting and piping, right? So we've done some redirection, right, where you send the output of a file, you send the output of a program to a file, right, or the output of a command to a file. And we've done some piping where you can send the output of one program to the input of another program. Sorry, command. Output of one command to the, oh, what's going on? Can I watch this week's? OK. And we've done some piping where you can send the output of one command to the input of another command. Now the question is can you do both? And the answer is yes, you can. Right? So if you think about it for a second, you might wonder, how are you going to do both, right? Because redirection, you're taking the output and sending it to a file, right? But with piping, you're sending the output to another process, right? To another command. So there doesn't seem to be a way to do both, but in fact there is. There's something called a T. Right? So the T command, all it does is it reads standard input. Right? So it reads whatever comes into its, it reads standard input, and it copies whatever it receives on standard input to standard output. Right? So in other words, you can connect another command to the end of the T. Right? So I can hook up another command over here if I want to. Right? But it also sends the second copy to a file. Right? So now you can do both. You can do both redirection and piping at the same time. Right? You can actually send it to more than one file if you want to. So you can copy the output to an almost arbitrary number of files, if you so desire. Normally, you just send it to one file. OK, so why might you want to do this? Well, it turns out it's useful if you want to save the intermediate results of a pipeline to a file somewhere. Right? And there's lots of reasons why you might want to do this. You might want it for debugging or logging purposes. Right? So you've written this big pipeline, and something funny is going on, so you want to look at the output at one part of the pipeline. Right? You just insert a T, and now you can look at the contents of the file. Right? You might want it for logging purposes, where you're just recording stuff. Right? It's also, I'm not going to show it to you today, but there is a way that you can use a T. Right? And instead of sending the contents to a file, you can send it to a second or a third or a fourth command. Right? So you can have multiple commands all hooked up to the end of a pipeline. You have to be a little bit careful when you do that. Weird things happen. But anyway, I want to save the date. I want to save the current date to a file, and I want to print the current year using the date command. Right? So let's look at this example here. Right? So date on its own. Oh, sorry, I didn't have to do that. Hang on. Alt-tab. So date on its own, right, outputs the date in a standard format, right? So if you read the man page for date, will on its own will output the date in this format, right? So the day, the month, the day of the week, the month, the day of the month, right? And then the time on a 24-hour clock, right? Time zone and the year. Right? So you always get that if you use just date on its own. Right? Now, what did I want to do in the first place? I wanted to save the current date to a file and print the current year. Right? So I want to extract the date. So I want to extract out Thursday, September the 16th. Right? And I want to send, and I want to print the current year. So I want to print 2021. Right? So what happens? Oh, that's not good. So what if I want, so I'm going to show you a T now, right? So I'm going to insert a T, and I think I'm calling this full date .text. Right? And so what happens here? Well, it looks like it's the exact same command, right? So it outputs Thursday, September 16th, blah, 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 right? But if you go and poke around with your file explorer, right, you'll see that somewhere there's a full date. Right? And you can see that T has diverted the output of date to a file. Right? OK, so that's great. That doesn't accomplish what I wanted to do, though. Right? I actually want to get the save the current date. So I want to save that date to a file. So I've got that part settled down, sorted out. I want to print out the year, though, at the end of the command. Right? OK, so how do I print out the year? So there's this command called cut. So cut will remove sections from each line of a file, right? And you have these options here. So what cut is really, cut is useful for is if you have text that has, text that's separated by delimiters that you know, right? So sometimes you have data that's organized in columns, right? Often in Linux or Unix, the columns are separated by tabs, so it's easy to get out the separate columns of the file. So you can use cut to do that, right? In this case, I'm going to use cut to separate out parts of the date that's output, right? Because the date, when you print it, is separated with spaces, right? So let me try taking the date, right? And I'm just going to pipe it to cut. And I think the slide says minus delimiter, delimiter equals space, minus field equals 1. Right, and so what cut does here, so the long option delimiter equals, and then you're allowed 1 character here, right? That says what delimiter cut should use to separate the tokens in your stream of text, right? So this is telling cut to cut things at the spaces, right? And then the field, in conjunction with delimiter, right, lets you pick which one of the fields, or it actually lets you pick multiple fields, multiple parts that were cut. It lets you specify which one of the parts of the text you want. Right, so field equals 1 gives me the first part of the outputted date. Right, so split at all the spaces, and then give me the first one. So that's Thursday. Right. If I ask for number 2, right, you're going to get September, and if I ask for number 3, you're going to get 16. Right. If you ask for number 6, that gives you the year, which is what I'm after. Right? So that gives me the year, which is what I wanted in the first place. Right? But I also want to output the date. Right? So date, pipe it to T, right? So that I can get the full date as a file. And then, right, continue the pipe and send that to cut. Right? So instead of using the long options, I'm now going to use the short options because it's a lot easier to type. The problem is the short options, they have a different format. So minus D is the delimiter. Now there's no equal sign. Right? It's just the delimiter after the D. Right? And now for the field, right, it's just minus F. And you can pick field number 6. Right? And now I get the output that I want on the screen. Right? I get the year. And if I print the full date, right, I get the full date, which is also what I wanted. So there is an example of a T, right? Now, you can insert these T's after any command, right, including after a T itself, right? So I can write a pipeline that looks something like this, right? So you know fortune randomly prints randomly prints a fortune to standard output, right? So I can take that and pipe that to T, right? What is T going to do? Well, T is going to take that text and save it to fortune.txt, but it's also going to send that text to the next thing in the pipeline, right? So it'll send the text to calsay, right? Calsay is going to pipe that to T, right? What's T going to do? Well, it's going to save whatever calsave output to cow.txt, right? Backslash and nothing after the backslash lets you go to the next line, right? So you have a very long line of code in bash. Backslash is how you break your lines. Right? So I'm going to take the output of T, right? So what is T output? What's the output of T? Well, it's just whatever calsay output, right? And it's going to send it back to calsay again, right? So we're going to have a cow that, hopefully we have a cow that speaks a cow that speaks a fortune, right? Hopefully. So let's see what we get. Right? So fortune, right? Random fortune. Fortune, pipe it to T. Right? Still prints out the fortune, right? Because it copies standard output. It copies its input to standard output and saves, right? So if I look at fortune.txt, indeed, that's what I get, right? I get the same thing. Right? Okay, now I'm going to pipe that to cow say, right? And now I've got the cow, right? Super. Now I'm going to pipe that to another T, right? Cow.text, right? So I get the cow, but I also get a file, right, containing the contents of what it just wrote to standard output. Now finally, I'm going to pipe that to, so backslash, enter, I can still type, that's great. So I'm going to pipe that to cowsay minus n. So cowsay minus n doesn't break the lines, right? And I can't break the lines because it's a long chunk of text that's going to get printed out, right? And there you go, right? So we've got our cow that says something that the cow said, and that's a very long quote, right? And if you wanted to, right, you can hook that up to another T, save that to a file, send it off to somewhere else, right? So if you really wanted to, right, we can pipe it to a T, right, cow2, right, and then pipe it to another cow, right, and now we've got 3 cows, right, and so on and so on and so on, right? So you can make these pipelines almost as long as you want. There is a limit, but it's pretty big, right? And you use a T when you want to when you want to copy output of a program to a file, right? Super. Okay. So for the time being, that's it for stream. That's it for pipelining. Right. So we've done some file redirection. We've done some pipelining stuff. I'm just checking the stream. File redirection. We've done. Yep, still there. Right. We've done some file redirection. Now we've done pipelines. We talked about T's. Right. We've been using ls a lot. Right. So on a Linux or a Unix file system, files are fundamental to the way the operating system works. Right, so now it's important to tell you about how Unix or Linux actually assigns permissions to different files. Right? So these Unix-like OSs, they were designed back in the 70s, well, starting in the 70s. Right? And they were designed for these what are called multitasking, multi-user systems. Right? So back in the 70s and 80s and early 90s, it would not be unusual to have one giant, well, not just one. It would not be unusual to have a giant computer or several computers centralized somewhere, right? And then many users connecting to those larger computers, right? So you wouldn't necessarily have a desktop everywhere, right? All the users would have a terminal, right? They'd have a keyboard and a terminal, and that would be connected somewhere to a large central computer, right? And you could have hundreds or thousands of people connecting, right? So you've got lots of users on one computer, right? So that's what the multi-user thing is, right? They're all doing something different, so that's the multitasking thing, right? Typically, the connections are done over a computer network of some kind, right? So it would be over a local area network back in the day. Now it could be the internet, right? Now, for this to work, right? Imagine you have your home computer and it's not just you on it, right? It's like 50 of your friends on it as well, right? What's the issue here? Well, you've got your own files that you may or may not want your friends to see, right? Probably don't want all of your friends to see all of your files, right? So there has to be some mechanism in place that protects users from each other, right? And also, there has to be some mechanism in place that protects the operating system from the user, right? So users should not be able to modify or perhaps even see other users' files, right? And it would be nice if an individual user could control who could see their files, right? Or who could modify their files, right? And similarly, a normal user should not be able to modify the critical OS files, right? So how does that work in Linux and Unix, right? So in a Unix-like operating system, there is the idea of an owner. So a user is allowed to own files and directories, right? So on your computer, whether you're on a Mac or if you're in Windows and you're using the Linux subsystem, right? Somewhere you've got a home directory, right? You, as the user, you're the owner of that home directory, right? And you own all of the files that are also inside that home directory, right? Probably. It's probably the case for most of you, and for almost all of you. Right? If you're on, so if, for example, if you're logged into the CAS lab system, right, you also have a home directory, right? You own all the files in your home directory, but the system administrators can go into your home directory and see what's there, right? So the system administrators have, they're omnipotent on a Linux or Unix-based system, right? They can do anything with any file. Okay, now the owner has control over access to their files, right, to their owned files. Right? Whatever files and directories they own, the owner can control certain permissions on those files. Right? So for example, it's possible for the owner to grant access to a file to all other users. Right? So I can say, look, this file here, anybody can look at it. I don't care. Right? This directory here, anybody can go into this directory and look in this directory. It's fine. Right? So the all other users, right, that's called the world in Unix. Right? Now, the granularity that you have with these permissions is not really fine. Right? So I can't say, I'm going to give permission to my friend Bob over here to access these files. Right? You can either grant access to everybody else, to the world, or you can grant access to what's called a group of users. Right? So there's this notion of a group, which is just more than one user. However, a normal user can't make groups. Right? So only the system administrator can create groups. Right? So there is a notion of permissions on files, but the granularity that you have is not very fine. Right? Okay, so how do you find out information about a user's identity? Right? In other words, how do I find out what group they're in, what their username is, and other things like that? Right? So the command ID is the command that tells you what their username is and other things like that. All right. Right. The command ID is the command that gives information about a user's identity. Right, so let's take a look at that. Yep. Right, so ID. Press enter, and it spits out all this information. Right. So UID equals 1000. Right, and it's in brackets my name, right? That's my user ID, right? So I'm user number 1000 on this computer. Ubuntu starts numbering at 1000. I'm the only user, so I get 1000, right? When you add the second user, they're probably 1001, and so on and so on and so on. The group ID is also 1000, so that's also me. So apparently I form my own group, right? And then you can see I'm in a whole bunch of groups, right? I'm in my own group here. I'm in the administration group, right? Because I'm the owner of my computer, so I'm also an administrator. And then these other funny things, CD-ROM, floppy disk, and audio, right? The group IDs are different, or the groups are different for every Linux or Unix-based system, right? Ubuntu uses the groups to help to make granting access to hardware easier, right? So for example, I'm a member of the group CD-ROM, so if I had an optical drive, I could actually access the optical drive, right, without doing anything special, and so on and so on and so on, right? You can ask for the information about a particular user. I'm the only one, so I can do that, and I get the same output, right? But on a large multi-user system, right, you can get information about all of the users on the system. Okay, so access rights. So a user has control over 3 different kinds of access rights for a file or directory, right? So you can control what's called read access. You can control what's called write access, and you can control what's called execution access, right? And these all mean different things depending on whether you're talking about a file or if you're talking about a directory, right? So if you're talking about a file, and if you have read access to the file, that means you're allowed to open the file and look at its contents, right? So I can open up for reading. Writing means you can write to the file, right? Or you can truncate the file, right? Truncate means set its size to 0, right? Interestingly enough, right, it does not allow you to delete or rename the file, right? So you should think about that for a second while I continue, right? You should think about why is this the case in Unix and Linux, right? In principle, you have the information to figure out the answer, right? But it may not have sunk in yet. Execute permission means you can run the file as though it were a program, right? Now, that doesn't mean you can run a text file like it was a program, right? So if I just have some plain text file with some junk in it, right, you can't run that as a program. If you try to run it, it'll barf, right? But if the file represents a program, you can now run it, right, if you have execute permission. You also need a read permission to run the file. Right? If you have a script, such as a Python script or something like that, it also lets you execute the script using the appropriate interpreter. OK, now directories. Directories are different. They're different than files. Right? So if you have read access on a directory, that means you're allowed to list the contents of the directory as long as you also have execute access on the directory. Right, so you need both read and execute access on a directory to actually list the contents of the directory. Writing means you can, you're allowed to create files in the directory. You can you can delete files in a directory, and you can rename them in a directory, as long as you have execute permission on the directory. Right? And why do you need execute permission on the directory? Because execute permission allows you to actually change to that directory. Right? So it allows you to actually type cd directory name and go to that directory. Now, if you have write permission on a file, right, why can you not delete the file? Right? Or why can you not rename the file? Right? So remember what a file is in Linux, right? The file name is not part of the file, right? The file name is part of the directory entry. Right? So the directory entry is the thing that maps a file name to the contents of a file somewhere. Right? It actually maps it to a inode. Right? And then the inode contains information about the file. Right? So in order to rename or delete a file, you have to go into the directory, right? Because it's the directory that keeps the file name information. That's why you need write permission on the directory to actually rename or delete a file. Good? All right, everybody got that? All righty? OK, so now if you're working on your own system at home, you probably don't have any files, right? Especially if you have, especially if you're using the Windows subsystem for Linux, right? Because it doesn't come with any files in your home directory, and it's probably the case that you haven't made a bunch of files there yet, right? But when you're trying things out, it's often useful to have a bunch of files kicking around, right? Organized in some structure, right? So there's a command called touch. And the touch command changes the access and modification times of a file, right? So if I touch a file, right, your file system will record the time at which I last accessed the file using touch, right? So I can update the time that I looked at it. It also changes the modification time, right? So you get the access and modification time. Now, if the file doesn't exist, you get an empty file, which is handy, right? So for example, in my home directory, I can do something like touch file1.txt. Now, I already have a, I already have file1.txt here. But at least I think I do. Maybe not. Oh, hey, look at that. I guess I don't. OK, so let's do it. Touch file1.txt. Right? ls file1.txt. Right? And there it is. Right? So we can get its size. Right? So you can see it really is 0. If I can type, sorry. So indeed, its file size is 0. Right? So I've got this empty file called file1.txt. Right? Now, it's also useful to make directories. Right? And I haven't told you how to do that. Not surprisingly, the command name is makedir, right? mkdir, and that will make it'll make the directories that you enter on the line now, right? So what am I going to call it? Dir, actually, hang on, let me check to see what I have here. lsdir star. OK, so I have dir00, dir01, dir02, and dir03. So I'm going to make dir1, right? If you want to, you can make a bunch of them. So I can do dir2, dir3, right, all in one shot. And now, if I do lsd star, right, I've got dir1, dir2, and dir3 now as well. Right? So I can make a bunch of directories. I can go into those directories, make a bunch of empty files, and so on, and so on, and so on. In a couple of lectures from now, you'll learn how to make literally hundreds of files and directories all at the same time, which is kind of cool. Not very useful, though, but it's kind of cool. OK. Now, if you want to find out what are the access permissions, what are the permissions on a file and directory, right, you can ask ls for them, right? And the way you do it is you pass in the L flag, right, for the long listing. So let's try that. So ls minus L. So that's going to list the contents of my home directory in long format. Right, you can see there's a bunch of files, a bunch of directories, and a whole bunch of information. Right? There's this long string of text over here. There's a number. There's my name twice. There's more numbers. There's dates. And there's names. Right? And to make sense of all this information, you need to know what all these different fields are. Right? You can ask for information about a particular directory. Right? So if I ask for what are the access permissions on dir1, what's in dir1? So that's actually asking you what's in dir1, right? And it says there's nothing in dir1, right? If you want information about the directory itself, you need to pass in the D flag, right? So the D flag says print out information about the directory but not its contents, right? So that gives me that. You can ask for information about a particular file, like that, right? The wrong one. Here. Okay. Good. All right. So when you run ls with the long output option, right, you get something that looks like this. Right. And now we're going to take this apart one piece at a time. Right. That little minus sign that you can't probably see at the back of the room, that's in red. Right. So the first character is the file type of file1.txt, right? These are the different file types that exist in Linux, right? So the dash is a regular file, right? File1.txt presumably is just a plain text file, so it's considered a regular file. If it's a directory, that character will be a D, right? If it's something called a symbolic link, that'll be an L. We'll talk about those later in the course, right? C and B, you're never going to see in your home directories, right? Probably you'll never see those, right? So C is what's called a character special file, right? And a character special file is a device. Remember what a device is in Linux, right? It's usually a piece of hardware, right? Or it's something that corresponds to a piece of hardware, right? So it's a device that handles data as a stream of bytes, right? And what does that sound like? Well, that sounds a lot like a terminal, right? So terminals, in fact, are files on your Linux file system, right? B is a block special device. Right? So that's a device that handles data as blocks. Right? What handles data as blocks? Well, your disk drive handles data as blocks. Okay? So your disk drive is actually a file on your Linux file system. Okay, so that's the first character. The next three characters, right? In this case, RW minus. These are the user read, write, and execute permissions that are on the file. Right? So the first character, file type, next three are the user permissions, right? So what do those mean? Right? If you see an R, that means the user has read permission. Oh, sorry. If you see an R, that means you have read permission, right? If you see a W, that means there's write permission, right? If you see an X, that means there's execute permission. And wherever you see a minus, that means the permission is not granted, right? So if I go back, right? On my file, file1.txt that I own, right, I can read it, I can write to it, but I cannot execute it, right? Okay, next three. So the next three are the group read, write, and execute permissions, right? So the group here is also the group named after me, right? But you can have other groups as well. It's, again, if you're just in your home directory, you're not going to see files that have different groups normally. Right, normally. But if there are groups, then these are the group read, write, and execute permissions. Right? The R, the W, the X, and the hyphen mean the same thing. So the group has read permission, but the group cannot write and the group cannot execute the file as a program. Right? Okay, and the last three are the world. Right? So everybody else. Right? These are the read, write, and execute permissions for everyone else. Right? So the world can actually read the file file1.txt, right? And that's the default behavior of Ubuntu, right? So the default behavior in Ubuntu is permissive, right? So a normal user, at least on this machine anyway, a normal user can, a different user than me can actually go in and look at this file, right? In CASLab, your accounts, I believe, only you can actually go into your own directory, right? Unless you change it otherwise, right? So you can go into CASLab and change your read, write, and execute permissions on your directories and let anybody see your files. Right? All right, the 1. That's the number of hard links. And we haven't talked about hard links yet, but we'll talk about those when we talk about symbolic links. So for now, all you need to know is that a hard link is a directory entry that associates a file name with an actual file in the file system. Right, so that's exactly what I told you a directory was, right? And it turns out it's these things called hard links that are mapping where the file name, which inode a file points to, right? A file name refers to, sorry. Right, and you have to have at least one hard link for every file, right, for the original name of the file. Right, so it's not surprising there's a 1 there. There is a way for you to add hard links to a file. We'll get to that a little later. The next one is the owner's name, right? That's me. The next one is the group name. Sorry, that's also me. Not that interesting right now. The next one is the file size. I think in blocks. In blocks, I believe. Right. So that's a fairly large file. The next one is the date. That's the modification time. It's the creation time if you've just created the file and you haven't done anything with it yet. It's the modification time if the file has existed and you've modified it somehow. Right? And then finally, of course, there's the file name. Right? All right, so now that you know about how to look at the permissions on a file or a directory, right, how do you go about changing them? Right? So there's this command called chmod. Right? Short for change mode, I think, but I'm not 100% sure. Change mod's a little weird the first time you see it, especially if you're using the numbers to change the mode. Right? So let's take a look at what's going on here. All right, so chmod uses octal numbers, right? Base 8 numbers. Right? And you'll see very shortly why it uses base 8. Right? But most people do not use base 8 in their regular lives. Right? At least I don't. Right? So what's base 8? Well, base 8, it's just a number representing using 8 digits. Right? So the digits 0 through 7. Right? All right, now here are the octal values. Right? So these are the numbers that you actually type in to the chmod command. Right? So I can use the numbers 0 through 7. Right? If you look at the binary representation of these numbers, right, things will start to become a little clearer, right? So 0 in octal is just 0, 0, 0 in binary, right? Right? 1 in octal is just 0, 0, 1 in binary. 2, 0, 1, 0, right? And 7 is 1, 1, 1, right? Now, imagine the zeros and ones to be false, ones to be true, right? And remember, your file permissions are read, write, execute, right? So if you see a 0, then you do not have permission for that particular field in the file permission. Right? So 0, 0, 0 means no, 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 right? 0, 0, 1 means no, no, yes, right? 0, 1, 0, no, yes, no, and so on and so on and so on. And that's why they use octal, right? But you have to be able to do the mapping to binary to actually understand what's going on, right? If you're a system administrator and you're doing this thing all the time, you just memorize what the octal values mean. The blue ones are the common ones, right? So some of these don't make any sense, right? So you can give write permission to a file, but not read or execute access. That's a little weird, right? You can write the file, but you can't read it. Strange, right? X, right? I can give execute permission, but I can't. But take away read and write permission. Also weird, right? And things like that. So 1, 2, and 3 normally not used. 7 is quite common. 6 is quite common. And 0 is quite common. Right? 5 and 4. Well, 5 is common for executable programs. I guess 4 is common for files that you don't want other people to look at. Right? Okay. So how do you use this command? Right? Well, you type in chmod, then you type in 3 octal digits. Right? And then you type in the file that you want to change the permissions of. Right? So 400, go back to the table, right? 400 is read, right? 0 is no permission, and 0 is no permission, right? So 4, give the user read access, right? 0, give the group no access, right? 0, give the world no access, right? So this makes the file private to me. Only I can read it, right? Let's try that out, see what happens. Right, so there's file 1, right? So right now, I can read to it and I can write to it. The world can, the group can read it and the world can read it. So change mod 400 file 1.txt. Right, list the contents of the file again, and now only I can read it. Right, I can read it. I can't write to it. I can't execute it as a program, and no one else has any permissions on it. Right. So there you go. So it's not too bad. Right. Grant read access to all users, right, and remove all other permissions, right? So change mod 444, file 1.txt, right? Remember 4 is read access only. So let's try that. Control L. Change mod 444, file 1. What am I doing? There we go. Right, and there you go. Now everybody has read access on the file. No one has write or execute access on the file. Grant all permissions to the user, which is common, right? So if I have an executable program, right, maybe one that I've written myself, right, then I want to be able to read it. I want to be able to execute it. I probably want to be able to write to it. So that's 7, right? If you want everybody else to be able to read and execute it as well, that's 5. Right? Or sorry, if you want other users to execute it, that's 5. Right? So 755, give me all permissions, give everybody else read and execute permissions. Right? And this is on dir 1. So let's take a look at that. So let's do ls minus ld dir 1. Right? So right now, actually that's going to be 755. Sorry, this is not a good example. 755 dir 1. It's not going to change anything. Right? I have read, write, execute permission on the directory. Everybody else has read and execute permission on the directory. Right, let me just change one of them, so 750. Right. So now the group has read and execute permissions on the directory, but everybody else cannot read or execute the directory. Okay. Now there's also the symbolic representation, which is easier to read but harder to remember how to use. Okay? So if you don't like the numbers, then you can use the symbolic notation. So the way this works is you pick one or more of these symbols from up here, you pick one from here, and then you pick another one from, you pick one or more from there. Or 0, I guess, yeah, one or more from there. Right? Okay, so if you pick U, that means you're going to change the permissions for the user. Right? If you pick G, you're going to change the permissions for the group. If you pick O, you're going to change permissions for the world. Right? If you pick A, that's the same thing as picking all of U, G, and O. Right? You're allowed to pick more than one of these. Right? So you can do UO, or you can do UG, or you can do GO. Right? And combine the permissions, combine the, I guess, the target, whatever group there, right? So if that's followed by a plus sign, you're going to add a particular permission, right? If it's followed by a minus sign, you're going to take away a permission. And if it's followed by an equal sign, you're going to assign the permission, right? And finally, which permissions are you going to grant or take away? R, W, and X, right? Read, write, and execute. Right? So we're going to pick something from here, something from here, something from here. Right? So change mod. Now if you pick nothing from the first table, that's the same as doing A. Right? So everybody. So change mod plus R pathname. Right? That adds read permission. Right? Adds read permission for all users to the file pathname. Right? So if a user does not have read permission, if group does not have read permission, then they will get read permission. Right? If they already have it, then nothing changes. Right? chmod u plus w, right? That's going to add write permission to the user, right? So the user will now have write permission on that directory. Sorry, on that file name, on fname, whatever fname is, whether it's a file or a directory, right? U minus x will take away execute permission on a file or directory, right? For the user, so I can do that because I'm the user, so let's take a look. Right, so on dir1, I have, right, execute permission on dir1. So if I use chmod u minus x, dir1, right? All right. I no longer have execute permission on that directory, right? What that means is I can't change to that directory, which is going to be a real pain in the butt, right, for me, right? Because I can't actually go into the directory to do anything now. Okay. Now, you can also assign the permissions, right? So if I say a equals rwx, everybody gets read, write, and execute permission, right? And now you can combine them as well, right? So with a comma, you can specify multiple changes at the same time, right? So chmod u plus x, give the user execute permission on fname. G equals rx, give the group read and execute permission on that on fname. Right, and so there's how you use chmod to control the permissions on your files and directories. Right. Okay. I guess I'll go for a couple minutes. So I'll go to quarter after. All right. So now there's that's all I want to say about permissions. That's all that you really need to say about permissions, actually. I now want to talk about something called expansions, and we've already used these, right? So you know that if you type in ls star, right, that'll list all the contents of everything in your directory, right? Okay, so when you type in a command and press enter, right, what does bash do, right? So bash sees a command, and then it sees some stuff, right? The stuff, right, bash might perform substitutions on the stuff before it actually executes the command. Right? So for example, if the directory has these 3 files in it, right, then ls star, right, that star actually gets substituted by the shell. Right? Star matches any file. Right? So the star gets substituted by a.txt, b.pdf, and c.out. Right? So that when bash actually executes the ls command, right, that's the command that gets executed. Right? So before ls gets executed, bash looks at the star, expands the star to everything that matches, right, and then calls the ls command with that input. Right? So that process of performing the substitutions is called expansion. There's 7 or 8 different kinds of expansion in bash. Right? And you need to know about all of them in order to get the most out of your bash shell. Okay. We've already used the wildcards, right? Star, question mark, the matching classes, the predefined classes, right? So expansions involving wildcards, not surprisingly, is called pathname expansion, right? Because it matches files and path names, file names and path names. Okay, there's a command called echo. Echo doesn't seem to do anything useful, right? All it does is it echoes whatever you type to standard output. Right, so it takes in some strings. It takes in an arbitrary number of strings as input, and it just echoes them. Or it prints them to standard output. Right? Not terribly useful when you're working on the command line, but it is useful when you write a script, right? Because you can use it to print something. Right? So if I echo, let's just try it. Echo hello, right? It just prints hello, right? So not that exciting. Right? But you can use echo to show pathname expansion in action, right? So pathname expansion occurs before the command is executed, right? So if I've got a bunch of files in my directory, so here I've got presumably file 1, file 2, file 3, and fruit.exe. If I type echo f star, right, what gets printed out? So let me just see what's in my directory. So I've got a bunch of files that start with f, okay? So echo f star, right? It's not going to print out f star. It's going to print out any file name that starts with f, right? So f star means match to any file name that starts with f, right? And that's what it prints out. Right? So there's your pathname expansion in action. Right? If you do echo file star.txt, right? That will print out all of your files that start with file and end in .txt. Right? And there they are. Right? If I change the star to a question mark, right? All the files that start with file and then have one other character followed by txt. Right? So I only have file.1 and files.text. How about echo f, what do I have here? Full. Right? FUL star is anything that starts with FUL. Right? Now, what happens if I echo something where the pathname expansion doesn't happen? Right? So I don't have any files that start with G. Right? So your choices here are it either gives you an error, right? It prints nothing, or it prints G star. And it turns out it prints G star. Right? So if there's no expansion that matches, it treats it as a string. Right? And that's pathname expansion, right? The other 6 or 7, I can't remember if there's 7 or 8 expansions we'll talk about on Monday, I guess. Right? And that's it for today. Thank you, everybody. Oh, if you don't know, assignment 1 is out. Right?